Hi everyone, my name is Lauren Byrnside,
And Grace Hozjan.
and this is our Physics 101 extra credit assignment. So let's get started. For our scene, we picked Spider-Man, the first Spider-Man from 2002, so we will play the clip for you guys. From our specific scene, from Spider-Man that we picked, we decided to do the part where Spider-Man is jumping over the building to catch Mary Jane as she's falling from the top of the building, and we are going to calculate the tension in the web during this scene and also other calculations prior to get to the tension that we are trying to calculate, and also determining whether this is possible in real life or not.
From the scene, we need to calculate and determine the total mass applied to the web from Spider-Man and Mary Jane. We need to solve for the time between the landing and the release, find the displacement when they both landed on the ground to when they were pushed back up into the air. We're going to utilize a kinematics equation to solve for the acceleration within that time frame. We're going to calculate the sum of total forces and to help aid for solving for the tension. And then we're lastly going to solve for the tension of the web and determine if that would be possible in real life.
From our objectives, we used the following equations from our Physics 101 course. We first used the kinematic equation shown here to find the acceleration, to then find the displacement and the tension. And then from here, we used the sum of forces, where we used to determine the tension of the force as well, of the web. From our step 1, we found the mass of each actor and actress from the movie Spider-Man. From our research, we observed that the total weight of Spider-Man, which is Tobey Maguire, was 71 kilograms, and Mary Jane, which is Kirsten Dunst, is 54 kilograms, which makes a total mass of 125 kilograms added to the tension of the web. From step 2, we observed the initial and final position time. From the clip, we observed the initial landing time here, shown in the image that we captured, and then the second image here was our final position captured, where we calculated the displacement. And when observing the movie scene clip time frame, we cut each part we wanted to observe, and that was found for the displacement, and we calculated the time as well using time frames from each position. And from the time frame calculated from each position, it was calculated to be 0.52 seconds.
Our observations of the initial and final positions, we determined that the displacement was 0.033 meters. In the scene, we measured Spider-Man to be 0.011 meters. But from some research, we realized that Tobey Maguire, the Spider-Man, is really 1.73 meters in real life. To determine this, we first had to measure the image with digital ruler to establish the distance in inches and then convert to meters. We did have to convert these measurements into a real-life scenario due to the observations being completed through a video screen. To do this, we took 1.73 meters times 0.033 meters divided by 0.011 meters to get 5.19 meters for the distance. These images are showing how we determined where to measure the displacement from. The bottom photo is showing the starting, and then the top is showing the finishing point. We then used a ruler to measure the distance between those 2 points, as well as the height of Spider-Man in the movie clip.
Step 4, we use the kinematic equation to find acceleration. We utilized the above kinematic equation here to determine our acceleration. So down below is our calculations. We plugged in 5.19 meters for the displacement and 0 to assume the initial velocity is 0 at the position, and half times the acceleration that we're finding times 0.52 seconds from the time frame squared to give us our calculation of 38.39 meters per second squared as our acceleration. In step 5, we calculated the sum of forces with our equation from our Physics 101 course, which is the sum of forces equals mass times acceleration. We plugged in our total mass of 125 kilograms times our acceleration that we found previously, which is 38.39 meters per second squared, to give us our total sum of forces, which was 4,799 newtons. Below is our mass times gravity to be plugged in to our next equation to find the tension, which we used 125 kilograms for our mass times 9.8 meters per second squared as our gravity to give us our force to determine our tension.
For step 6, we were starting to find the tension of the web. To find this, we created a free body diagram to determine the sum of forces in the y direction. The sum of forces in the y direction should equal 0 due to there being no acceleration occurring at the resting position. We took the net force equals tension minus gravity to solve for tension. So 4,799 newtons equals the tension minus the gravity of 1,225 newtons to give us the tension to equal 6,024 newtons. Our final question was, can this scene occur in real life? From our calculations and observations, we determined that this scene could occur in real life. It is known for a rope to withstand several thousands of newtons of weight before beginning to break. This does depend on the specific type of material used to create the rope, but in most situations this would be able to occur. Thank you for watching our presentation.